Hi everybody, this is lesson 3.1 for Algebra 1. This unit we're talking about systems of equations, and so today we're going to talk about how to solve a system of equations by graphing. We'll start out with just some of the basics of what is a system of equations, what does a solution to a system of equations look like, and then how can we go about finding that solution by graphing. So we have some vocabulary here. So when we talk about a system of equations is just a group of two or more equations. All right, that's all it is. It's just we're talking about two equations, two or more equations. You could have a system of 3 equations or 4 equations, but for our purposes, we're going to be talking about a set of 2 equations, and then also for our purposes right now, we're only going to limit that to linear equations. Okay, a system of equations can be any kind of equations, but we're going to limit our discussion to just linear equations, since that's what we're most familiar with. So all that means is that we have a group of 2 linear equations, and if we were to graph those, we would graph those on the same coordinate plane and see how they interact. And when we talk about a solution to a system of equations, a solution is just simply the points that they have in common. Okay, they could have many points in common. They could have 1 point in common. They could have no points in common. But our solution is the shared points, right? And what that looks like on a graph is it looks like where those graphs cross. So where the graphs cross, that's our solution, and our solution is going to be a coordinate in this case. It's a coordinate, an XY pair. So let's take a look at an example. So here we've got 2 lines. So I can tell that they're linear equations. I can tell they're lines because they're in the format of y equals mx plus b. So I can see that my m value here is -1/2 and my b value is 5. So that tells me that that's a linear equation, the fact that it can be written in that format. I can also tell because the exponent on my variables is 1, right? There's no variable there, so we consider that to be 1. I'm not multiplying variables together. I'm not dividing by variables. I'm not taking a variable and raising it to the 2nd power or the 3rd power or anything like that. So I can tell that those are linear equations. So here I've got 2 linear equations, so we call this a system of linear equations. We've got 2 of them there. And so I'm just going to graph them, and let's see what they look like. I can tell that this line here starts at 5 on the y-axis. That's my y-intercept, and so that gives me that point, so there's my point to start with. And then it has a slope of -1/2, so that means every time it goes down 1, my rise is 1, my run is going to be +2. Down 1/2, down 1/2, down 1/2, down 1/2, and so I can kind of map that line out. And I'm going to extend it on the other side here, just to show that it goes forever in both directions. Alright, so there's one line, and then let's graph the other line. So if I take a look at the other line here, we'll make it blue. And so I can tell that this line crosses the y-axis at +1. So it crosses the y-axis at +1, right, so that point 0, 1, and then it rises by 3 every time it runs 2. So rise 3, 1, 2, 3, 1, 2, let's see, did I do that right? 3/2. Oh, yeah, rise is 3, 1, 2, 3, runs 2. Yeah, 1, 2, 3, 1, 2. Okay, so I can see that line there, and I can extend that line out, and I can tell that that line goes. But what I'm looking for here is where those lines cross, and I can see that those lines cross right here. Right, they cross right there at that coordinate, and that coordinate is the point 2, 4. So I would say that those lines have a solution of 2, 4. Okay. Notice again that our solution here is a coordinate. It's not just a number, right? It's a coordinate, and the location is 2, 4. So 2 along the x-axis, 4 on the y-axis. So another situation. We've got this equation, right, y equals negative 1/2 x plus 5, and actually I recognize this. This is actually the same line from the last example. So that red line, it starts at 5 on the y-axis and has a rise of negative 1 and a run of 2. So I got a pretty good idea what that looks like. So let's go ahead and graph it real quick. It starts at 5 on the y-axis, and then it goes down 1 and over 2, down 1 and over 2, down 1 and over 2. And so that looks like it goes like that. I'm going to adjust that line here, extend it out the other direction, and that looks pretty good to me. Okay. Now our blue line here is a little bit different. So this one is not in slope-intercept form, so we still have to graph it. There's a number of ways you can do that. You could put it into slope-intercept form, so you could solve it for y, get the y value all by itself. Subtract x from both sides, divide everything by 2. You could also just build a quick table of values, right? I can just look for some couple of values, and in this case it's pretty easy. I can just look for my intercepts. Those are generally some good points to kind of start with. And so if I look for my x value to be 0, okay, I can say, well, what will my y value be? If my x value was 0, I'd have 0 plus 2y equals 8. So I'd have 2y equals 8, which means that y would have to be 4. And so there I've got 1 point already. I can look for another point here. Let's say that I put 0 in for y. If I put 0 in for y, right, this would be my x-intercept. So what would the x value be when y is 0? Well, this would just be x plus 0 equals 8. So I can see here that x is equal to 8. And so now I've got 2 points. I can go ahead and graph that. So I know it goes through the point 0, 4. Change my color here. Goes through the point 0, 4, and it also goes through the point 8, 0. So there I have my system of equations. And I can see that it looks like those lines are not going to cross. Okay? And if I look at the slope of this, if I go from say like this point to this point, I can see that it also goes down 1 and over 2. This also has a slope of negative 1/2. These two lines have the same slope. They have different y-intercepts, but they have the same slope, so we know that those lines are parallel. When those lines are parallel, that means that they never cross. That's just the definition of parallel lines. Parallel lines are two lines that don't cross, and so when we talk about a solution involving two parallel lines, they don't cross. So we would say that there is no solution. So there is no solution here. Oops. So this would have no solution. And in MyOpenMath, they'll ask you to type this DNE, right? That stands for does not exist. So the solution to this doesn't exist. There's no solution. Let's look at one other example here. Here I've got two equations again, and again I'm starting to recognize this line here, right? That's the same line we've kind of been playing with. It starts at 5 on the y-axis, has a slope of -2. So got some practice now. Get this line in here pretty quickly. Okay, so there's that line. And now I come back here and I'm back to this blue line, and now I'm going to try to graph this. And again, I could put it in slope-intercept form. I could move things around, but it's in standard form, and it looks like, you know, I can figure out a couple of points pretty easily here. So I'm going to put 0 in for x. If I put 0 in for x, I would have 4y equals 20, or y equals 5. Sorry, let's see, 0 in for x, I would have y is equal to 5, yeah, y is equal to 5, so 0, 5. And then if I put 0 in for y, put 0 in for y for here, the 4y will go away, it will become 0, and so I would have 2x is equal to 20, and so I'd have x is equal to 10. So there I have a couple of points. I have my x-intercept and my y-intercept, and so I can go ahead and build that line. Change the color to blue here, and go ahead and graph this line. I can see it goes through the point 0, 5. Well, that's right on that red line. And then the other point is 10, 0. Look at that. Those lines are actually right on top of each other. Okay, so I actually happen to come across two lines that are exactly the same. And you can verify that. If you put this line into slope-intercept form, you'll see that it has this same form. It has the same slope, it has the same y-intercept. These two lines are the same thing. They have the same slope, they have the same y-intercept. We would call those lines congruent lines, or they would be lines that are on top of each other. We call them the same lines. So for a solution, right, for a solution we would say there's an infinite solutions to this one. Okay. What are the points that they have in common? Well, they have all of their points are in common. There's an infinite number of points on there that they have that belong to both lines. And so this is be infinite solutions, or they'd be the same lines. Okay, so we have three cases that kind of pop up here from time to time. And so they kind of categorize these by, first, whether or not they cross. Okay, so if lines cross, we call them consistent. Okay, if they cross, if they have at least one solution, we call them consistent. And if they don't, we call them inconsistent. So a set of parallel lines would be inconsistent. They don't have any points in common. Okay. If they're consistent, right, if the lines have at least one solution, then we know it can be either two cases. They can either have exactly one solution, or they can be the same line and there would be an infinite number of solutions. So if there's only one solution, we call that independent. And if there are an infinite number of solutions, if they're the same line, we call that dependent. Okay, so we'll kind of use these to talk about these. You'll hear these terms, right? You'll say, oh, this is a system of equations that's inconsistent. Well, that tells me that they're parallel lines. If I say, well, I have a system of equations that's consistent and independent, I know that there's only one solution to that, and they only cross in one place. So I have a little kind of flow chart here that kind of helps you categorize lines. And so you can just kind of go through this and you say, well, do my lines cross at least once? If no, if they don't, then they're inconsistent. And that's all we say. We just say that they're inconsistent. That means that they're parallel lines and there's no solution. If they do have at least one solution, then we would say, yes, they're consistent. Okay. And if they're consistent, how many solutions do they have? If they have one, that would be independent. So we would say that system is consistent, independent. And if they have an infinite number of solutions, we'd say that system is consistent and dependent. Okay, so if you need to pause the video right here and kind of walk through that and write that down, feel free to do that. If we go back and look at our previous examples here, okay, so here we have a system of equations that has exactly one solution. So we would say that this is consistent, it has a solution, and it's independent. Okay, consistent and independent. Okay, the values of one the values in one equation are not dependent upon the values in the other equation. They just happen to have one point in common, but they're not dependent upon each other. This one has no solution, so we would call this one inconsistent. Okay, no solution, parallel lines, so that system is inconsistent. And then this one is an infinite number of solutions. So we would say that this one is consistent and dependent. Okay, so it's both of those. It's consistent and it's dependent. The values in one equation actually are dependent upon the values in another equation. They're all the same, so that's how we name that. Now, yesterday we were looking at some situations here where you might have some what are called constraints. Okay, so when we have a constraint, it says, well, this has to happen and this has to happen. And so we're looking at two qualifications here, right? Two constraints. It says that this has to happen and this has to happen. And so we looked in our Desmos activity yesterday, we looked at two numbers that had to add up to be something and that had a difference of something else. And so what we'd like to be able to do is to turn that into a system of equations. And so if I did that, if I looked at this situation here, it says I have two numbers that have a sum of 13 and a difference of 5. Sum of 13 and a difference of 5. So what does that mean? Well, I'd like to write this out as equations. I could kind of guess and check my way through this, maybe, right? If it was an obvious answer or an easy to get to answer. But I don't know that it is, and I don't even know if there's an answer to this. So what I'm going to do is I'm going to write a system of equations to check that. So I'm going to say my first number is x, and my second number is y, and it says that I have two numbers that have a sum of 13. So sum of 13 means that when I add them together, x plus y, it has to add up to be 13. And then, so that's my first constraint. My second constraint is that the numbers have a difference of 5. That means when I subtract the numbers, I get 5. Okay. So there I have a system of equations. Okay, and I could graph that system of equations and figure out what those numbers are. So if I were to graph this one, let's start with the red one. So let's just pick a couple of numbers here. Actually, let's do this a different way. Let's go ahead and put this in slope-intercept form. And so if I put it in slope-intercept form, I'm going to get the x to the other side. So I'm going to subtract x from both sides. And then I would have negative y is equal to negative x plus 5. Okay, and it's almost slope-intercept, but I don't want negative y, I want y. So I'm going to multiply everything by negative 1. I'm going to take this whole thing, I'm going to change all the signs. I'm just going to multiply everything by negative 1. And so here I would now get positive y, which is what I want. Negative 1 times negative y gives me negative 1 times negative x gives me positive x, and negative 1 times 5 gives me negative 5. Okay, so there's an easy to graph solution there, an easy to graph equation. I know that my y-intercept is negative 5. I know that my y-intercept is negative 5. And it has a slope of 1. So every time it goes over 1, it goes up 1. And so I can map that out. It actually goes right along the grid dots there. I'm going to extend it this way. Okay, so there's my red line there. Okay. If I go back and look at my my black ones here, right? So if I move these around and I subtract x from both sides, so if I subtract x from both sides, minus x, then I get y is equal to negative x plus 13. Okay. So I can see that this crosses the y-axis at positive 13 and has a slope of negative 1. And so if I go to graph this, well, I run out of room on my graph. I don't have 13 up here. So what can I do? Well, I can just figure out a different number. I can say, well, what if x was 4? Let's say that x is 4. So I would say that if my x value was 4, I'd have negative 4 plus 13. That would be my y value is 9. Okay. So I have my point there. I have a point there. So 4, 9. So 4, 9. Let me graph this. So 4, 9, right? So there's my line there. And it has a slope of negative 1. And so it's going to go down 1 and over 1. And so even though I don't have the y-intercept on my graph, I can still start at any other point that I want to. And when I look at this solution, right, I can see that, well, it looks like 9.5 is kind of my x value, and 4.5 is my y value. Again, I want to make sure that I've graphed this accurately and that I have my points on there accurately, but I can see right there that it looks like about 9.5 and 4.5 are where my points are. So I would say my solution here would be, at 9.5, right? 9.5, so what is that, 9.5? Is 19 over 2. And then 4.5, so that's going to be 9 over 2. So that would be my solution. So two numbers that add up to 13, 9.5 and 4.5, and have a difference of 5. 9.5 minus 4.5 gives me 5. So that actually works out. I would say that this system of equations here, we would call this consistent and independent. Consistent, independent. Okay, so I'm going to go ahead and leave it right there. Take a look at the problems in your homework, and let me know if you have any questions.